Welcome to calculus. Let's begin our journey through calculus with the question of the tangent line. So what is the tangent line? The tangent line is a line that is tangent to a given curve, say y equals x squared at a given point. How about the point 1, 1? Okay, so there is one and only one line that is tangent to this curve at this point. It's going to look something like this. The tangent line shares the point 1, 1 with the line, and it's the only point that it intersects the curve with. Okay? So the tangent line does not go through the curve, and it does not intersect the curve at more than one point. So we need to get the equation of this line. So the equation of a line is y minus y1 equals mx minus x1. Now, we have x1 and y1, 1, 1. All we need is m. So recall that the equation for m, the slope is rise over run y2 minus y1 over x2 minus x1. All we need to get the slope is a second point, and then we're done. So for the second point, oh no, we don't have one. This is where the difficulty comes in. So how do we make progress here? We are in effect stuck because the line in itself only shares the one point with the curve. We don't know anything else about it. What we can do is use the curve to approximate a second point. Okay, that's all we have to go with. However, the key idea is that the closer we are to the point on the curve, the better the estimation is going to be of the slope. So if we consider the following point, okay, it's fairly close, and we can connect those 2 points. And when we do, we get what is called the secant line. So the secant line is simply a line on a curve that connects 2 points. Okay, let's put an equation up here. So for the secant line, the slope, what we're going to write, instead of y2, well, that's x2 squared. And we subtract 1 because 1 squared is 1. And that's going to be over x2 minus 1. So now we can approximate our slope by selecting a second point on the curve. So we want to pick points that are close, and let's make it easy to start with. Let's go ahead and choose for our first slope the nice integer point 2, 4. Okay, so if we square 2, we will certainly get 4. And 4 minus 1 is 3. 3 over 1 is 3. So first estimate is 3. It's not a good estimate for the slope because 2, 4 is a little high. So let's pick a second estimate and let's get much closer. So for a second estimate, now let's use 1.1. Okay, now this is actually close, right? 1.1 is close to 1. And what do we end up with for our second slope? Well, if we square 11, that's 121, so this would be 1.21 minus 1 over 0.1. So we get 0.21 over 0.1, multiply numerator and denominator by 10, and you get, for a second slope, a nice 2.1 estimate. Okay, pretty good. Can we do better? Certainly, 1.1 is not the closest number to 1. There is no closest number to 1. So to get a little bit closer, how about we try 1.01? Okay, so we're going to square 1.01, and let's see what we get. Okay, so for this next point, if you square it, you're going to get a 1.0201, okay, over 0.01. And so for 0.021 over 0.01, multiply numerator denominator by 100, and you get 2.01. Okay, we're making good progress. What we're doing is we are approximating the slope of the tangent line by choosing values for x2 that are closer and closer to our x1. Okay, we chose 2, 1.1, and 1.01. And it appears that the slope is getting closer and closer to 2. And actually, if you pick closer values like 1.000001, you will get a slope of about 2.00001. And there is no limit to this process. So, how can we find an exact solution? Is the slope of this tangent line exactly 2? Let's try to look at it in a slightly different context. So let's call this first point x, and let's call this second point x plus h. Now the idea is h is just a little more than x. Okay, it was 1, it was 0.1, it was 0.01. Now let's go ahead and recast the problem in terms of x and x plus h. So if we do that, we will get a slope of what? Let's use functional notation, okay? So we've got f of x equals x squared. Now the second point is actually our x plus h. So it's the function at x plus h. Those are the first, it's being squared. Jumping ahead here. The function squares it, we're not squaring the function. Okay, and then we're going to subtract f of x. And this is all going to be over what? Well, our second point is x plus h minus x. Okay, this is just y minus y over x minus x, using the points x and x plus h instead of x1 and x2, using functional notation. Okay, that's good, and we can simplify this a little bit further to say, well, this is now f of x plus h minus f of x all over h. Okay, looks pretty good. So how is this helping us? Okay, what we want to do, we want h to be as small as possible. Right? The smaller h's, the better the approximation is of our tangent line. So can we get it perfect? Well, we could get it perfect if h could be 0, right? But if h is 0, the function collapses. You know, if x2 is x1, the function collapses. Okay, so it appears like we're stuck. However, what we can do is we can go ahead and use this definition of slope with this particular function and see what happens. Okay, so we're going to apply this definition of slope here. And f of x plus h is simply x plus h squared. So now we're looking at this parabola minus f of x, that's x squared, all over h. Now we can simplify by multiplying out. We get x squared plus 2xh plus h squared minus x squared, and that's all over h. Now you can see that the x squareds cancel, and we are left with 2xh plus h squared over h. Okay, now the idea is we want h to be 0. We want it to be as small as possible, and we can keep making it smaller and smaller, and you can always do that. You can plug in any small value, but you cannot plug in 0. Okay, the whole thing collapses. It's not defined. It's undefined. It's not in the domain. But now, with this next step, you can cancel out an h, and you get 2x plus h. And now, you can plug in h as 0, and you get m equals 2x. Okay, this is a little bit interesting. What have we done? Okay, what we've done is we have used this definition of slope, just y minus y over x minus x in functional notation using x and x plus h, applied to this function x squared, and we find that the h cancels, thereby allowing us to plug in h equals 0. Now, does this give us something sensible? Well, at the point 1, 1, using functional notation, we can write this is equal to 2 times 1, which is in effect 2. So what this shows is that the slope is precisely 2 when h goes to 0, which is what our approximation showed. Now, does it work for other points? Well, let's try m of 0. What does this mean? What m of 0 means is you want the slope at the point 0, 0 of the tangent line. Well, clearly the tangent line here is the x-axis. It is y equals 0. And if we plug in, we get 2 times 0, which is 0. Okay? That's looking good. Let's try one more point. What about negative 1? What is m of negative 1? Let's find out. So if we go up to negative 1, we get a mirror of our point 1, 1, and the tangent line is going to be something like this, and we get 2 times negative 1, and that is negative 2. So what we have done is we found not just the correct slope for the tangent line for y equals x squared at 1, 1, we've actually found it for every single point on the curve using a general definition that will apply to any given function. But hold on. This h can't be 0, it's not in the domain. Now h is 0 and it works is a little bit suspect. And the true story is that Isaac Newton just did it. Because he said it works, this gives me what I want, this can do the physics that I need to do. And mathematicians after him said, hold on, you cannot just do something like that. You must precisely define everything, and h is not in the domain, but it does seem to work, so how can we resolve this? There was not a way to resolve it before the mathematics of calculus. The way that it has been resolved is to define something brand new. Okay, that something new is something where you may have a value like 0 that is not within the domain, but if you can get arbitrarily close to it, you can, in effect, find the precise answer by allowing it to go to 0 if the algebra works. And that concept, which we will explore in depth, is called a limit. So if you take the limit as h approaches 0 of f of x plus h minus f of x all over h, that is the definition of the derivative. And what we found, this m equals 2x, is the derivative of the function x squared. And what it delivers is the tangent line. Really, it's the slope of what? Of all the tangent lines at every single point on the curve. That is the geometrical interpretation of the derivative. It gives you every single slope at the curve at every single point of the tangent line. And just to finish out the original question, what was the equation of the line? Well, now we can plug everything in. We have y minus 1 equals 2. We got a slope of 2, x minus 1. So that is the equation of the line. You don't have to put it in y equals mx plus b form. This is the resolution to the question of the tangent line, which is a famous question within the history of math. And this definition of the derivative will stay with you throughout your study of calculus. And what's coming next is a discussion of limits.